This is 5.3, exponential functions, and let's take a look at the difference between two different types of functions. So here's one function, f of x equals x squared, and here's the other function, f of x equals 2 to the x. Now you'll notice that these both have a base, and they both have exponents. So you might say, well, they're both exponential functions. There's a big difference between these two. In the first one, the exponent is a constant, and the base is the variable. In the second one, the exponent is a variable, and the base is the constant. And this is a big difference between the two. You can maybe see this difference when you create a table. So you can see that these are different functions. Initially, in the early numbers, 0, 1, 2, and 3, x squared grows pretty fast. But as you move on to bigger values for x, for example, 5, 2 to the x is growing faster than the x squared, and it will continue this way. So this is what we mean by an exponential function. Exponential function has the variable in the exponent, and the base is a constant. That's an exponential function. So let's talk about this base. If we look at the example that we just wrote, 2 to the x power, and if we were to graph this using the table of data that we generated over here. So let's look at this table of data, and let's plot some points. As you move to the right, you get a shape that looks kind of like this. What happens if we move to the left? So what we would need to do is pick some negative values like -1, -2, -3, and find out what those are. So if we did -1, -2, -3, we would get 1 over 2, and 1 over 4, and 1 over 8. Because remember, negative exponents reciprocate. And so that means we'd have -1, 1/2, -1, 1/4, or -2, 1/4, -3, 1/8. So the graph does something like this. How does that graph behave as you go out to the left? The y values get closer and closer to the x-axis, but they never cross it. So there's an asymptote there. A couple other interesting points on this. This point right here, this is 0, 1. The other important point is this guy, 1, 2. And if you look at the table and how we came up with these, here's the 1, 2, and here's the 0, 1. Remember those rules we talked about? Anything to the 0 power equals 1, and anything to the first power equals itself? That's how we got these 2 points. We used those first 2 rules. This, by the way, is your basic, everyday exponential function. X minus h squared equals 4p y minus k. Remember that? In your vast experience of using h and k's, what variable was h associated with? It was always associated with x, right? So if we were to add an h to our existing equation up here, and I'm going to rewrite this as y equals b to the x power, where would you suggest we should add the h? So let's do x minus h up there. That's your horizontal shift. We're just going to put a plus k here. And there is h and k. So now we've taken our standard exponential function and we've added a horizontal shift and a vertical shift. There's one more thing we can add, a scaling factor. This is the complete equation of an exponential function. B is called the base. H and k, you know about these guys. These are horizontal and vertical shifts. And a, it is a scaling factor, but when it comes to exponentials, a has a special property. It's called the initial value. It is also the location of the y-intercept, given that there's no like h and k shifts, and we'll talk about that a little bit. One point of clarification on the base. If b is greater than 1, then you have exponential growth. If your base is greater than 1, then your function is growing as you move left to right. If your base is in between 0 and 1, you have exponential decay. which means the function decreases as you move left to right. And a growth function looks like this. A decaying function looks like this. It starts up really tall, zips down through the y-intercept, and then hugs the x-axis as you go to the right. A table below shows the values for the function f of x equals b to the x power. They want you to identify the base. So you have f of x equals some number to the x power. What is that number given these set of y values? And maybe you don't like how this is written. So what is the base? Yeah, and you just kind of look at this guy right here. Here is rule number 1. Anything to the 0 power is equal to 1. And here is rule number 2. Anything to the first power equals itself. So you have x to the first power equals 4. What does x have to be? Has to be 4. So really, we don't need to look at this data or this data. We need to look at this one, and then this one gives us the base. And we can do the same thing in the next set of data. What is the base of the second set of data? It's going to be 6, because we're going to say anything to the first power equals 6. Right? That's what this column says right here. We're still not dealing with horizontal and vertical shifts yet. No H and K's, okay? But we do have a base. Look at that first one. We have a base, and we have an initial value. You'll see in the homework these are drop-down menus. And the first one says, what type of function is this? The function type. And so your options are going to be exponential and linear. When you look at that first function, what type of function is that? Is that an exponential function, or is that a linear function? Yeah, so we're going to say exponential. The second one, linear. The third one, exponential. The second drop-down menu asks, is the function increasing or is it decreasing? And so when you look at the first function, is that function increasing or decreasing? Yeah, it's increasing. And how do you know it's increasing? Because b is greater than 1. That base is greater than 1. So that means this function, that first function, is exponential growth. The next one, function g, that's linear and that's decreasing. How do you know it's decreasing? Because you've got a negative slope. And then if you look at the third one, increasing or decreasing? Yeah, it's also increasing. And it's increasing because, again, your base is greater than 1. So then in the second column it says what's the slope or the base. So this drop down is going to say base, and our answer is going to be 4. This is going to say slope, and our answer is going to be negative 23. And this is going to say base, and our answer is going to be 1.2. Vertical intercept. What's another name for the vertical intercept? The y-intercept, yep. Let's do the line. That's pretty easy. The y-intercept is going to be 0, 180. Take a look at the first one. So what is going to be the vertical intercept? And remember, 2 things. Number 1, all functions go through 0, 1 unless there's a scaling factor in front of them. So maybe one way we could figure this out is by making a table of this function. So here's y, and d of y equals 7 times 4 to the y power. So let's put in 0, 1, 2. So 4 to the 0 power is 1. And if that's all we had, that's your point 0, 1. But we have more. We're not done. It's not just 4 to the 0 power. It's 7 times 4 to the 0 power. So that means it's going to be 7 times 1, which is 7. So that's going to give us 0, 7. So that's our initial value. So if you were to graph this guy, 0, 7 is up here. It is still exponential growth, and it still is going to hug that x-axis and then shoot up like that. So what is the vertical intercept? 0, 7. Go down to the third one, and now this should be pretty easy now that you know how to play the game. 0, 1, 10. Your y-intercept is actually your initial value. without any horizontal vertical shifts. Okay. Later we will get into horizontal vertical shifts and it's going to change things. You're looking at the function off to the right. What is the initial value of that function? 1378. That's the initial value. That's also the y-intercept. Right? So way up high at 1,378, that's your y-intercept. What is the growth or decay rate as a percentage? And this is starting to get away from pure mathematics and more like application. Growth rates, percentages. 0.06 is the correct decimal, but they want it as a percentage, so I'm going to go 6%. And this is going to be growth. Put this into context. Let's say that you had a petri dish of bacteria, and that petri dish initially contained 1,378 bacteria. And every hour, your bacteria grew by 6%. What would your population be after 3 hours? You put a 3 in for X and it'll tell you. That's what this equation does. All right, let's do the next one. The initial value, 4541. Growth or decay? It's growth. You took the base, you subtracted 1, and you got a 3, which is a decimal. You move the decimal 2 spots to go from a decimal to a percent. It's the same thing. You took 1.06, subtracted 1, and got 0.06. Okay, that's cool, but that's a decimal. We now need to go percent. So we move that decimal point 2 spots, and you get 6%. You take your base of 4, you subtract 1 to get 3, and then you convert that to percentage. All right, let's do one more. So here is your original amount, 1643. We're going to take this 1.095. We're going to subtract 1, leaving us with 0.095. That's decimal. Then we go percentage by moving it 2 spots. 9.5% growth. Initial amount, easy, 2360. Growth or decay? Decay, it's between 0 and 1. How much decay? 0.71 minus 1, which is negative 0.29. And the negative means decay, right? So you just kind of get rid of the negative and you say 29%. So again, the initial value, the y-intercept, is 3460. This is going to be, again, a decay because you looked at the number and you saw that it's between 0 and 1. How much of a decay? 3% decay. Now you make the formula. Initial value is 204. What's my base? I have a 7.5% growth. 1.075 to the x power. 0.075, 2, right? Convert it into a decimal, and then add it to 1. And why 1? Because 1's 100%, right? Okay, next one. 696, that's easy. 2.13. Why? Convert this into a decimal, 1.13, and then add 1. 1251, and you have a decay rate of 30%. A 30% decay rate is 70% of the original amount. The item that you're purchasing is $1,251, and it's on sale for 30% off. How much of the original amount are you paying? 70% of the original amount. So 1583 goes here. Decay rate is 9%, so what goes in the parentheses? 0.91. So let's go through 1, 2, 3, and let's do each row for the 3 columns. So initial value for the first column, 800. For the second column, 700. For the third column, 650. Done. What's the base? And now they're not asking for a rate, right? So they're not saying like what's the growth rate or anything like that. Just straight up, what's the base? 2, 0.7, 0.35. What's the domain of the exponential function? Range. 800 times 2 to the x power. That is going to have an initial value, a y-intercept at 800. And if you wanted to, you could do this, x and y in 0. So 800 times 2 to the 0 is 800. 1 is 800 times 2 to the first, which is 1600. 2 is 800 times 2 to the second. 2 to the second is 4. 4 times 800, 3200. Negative 1 is 800 times 2 to the negative 1, which is 800 times 1/2, which is 400. So at negative 1, this is at 400. And then it'll be divided by 4, 200. And divided by half again, 100. Half, 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 but it'll never get to 0, right? It'll get close, it'll never get there. So what is the range of this? What are the y values? 0 to infinity with a parenthesis on the 0, because it never gets there, right? It never gets to the 0. So we're going to go 0 to infinity, 0 to infinity, 0 to infinity. The only time it will not be 0 to infinity is if we have vertical shift. What is the horizontal intercept? In other words, where does it go through the x-axis? At D and E, right? It doesn't. Where does it go through the vertical intercept? Oh, that's your initial value. So 0, 800, 0, 700, 0, 650. Where's your horizontal asymptote? Remember on this graph, there's a horizontal asymptote right along here. That's where your horizontal asymptote is. Is there a vertical asymptote? No, no vertical asymptote. What is the left to right behavior? And if you hit this drop down, it's going to say growth or decay. So when you look at that first one, is this a growth function or a decay function? And how do you know it's growth? Because the base is greater than 1, right? So this tells us we have growth. What does this base tell us? Decay. And what does this base tell us? Growth. It's important that you start to create a picture and again go back and forth between features of the equation and features of the graph. The graph helps you understand why the equation is built the way it is, and vice versa. Understanding the equation lets you know how the graph is built. If you wrote this value here, this dot, will always be 0a, whatever that initial value is. If we put a 1 here, this value here will always be 1ab, because b to the first is itself, and b times a is ab. So these are 2 points that you'll always be able to plot. Now a little bit later on, when we get into more advanced graphing, we're going to throw h and k in here, right? But all you do when you throw in h and k, think about this, we're going to put a minus h and a plus k here and here. All you're going to do is grab this point and this point, and you're going to shift them both up or down or left or right. These 2 points are very important, and remember where they come from. Anything to the 0 power is equal to 1. Anything to the first power is equal to itself. Those 2 points come from that rule.